Welcome back to the Deep Dive. We're here to give you that ultimate shortcut to being well-informed, and today we are jumping right onto the modern factory floor.
We are indeed. Our whole mission today is about intelligent industrial automation. For you, the listener, this is really about understanding how factories are. Well, they're not just assembly lines anymore. They're becoming these complex, self-optimizing ecosystems.
And the pressure to do this is it's monumental. It's not about small incremental gains. Manufacturers, they need to guarantee maximum uptime, boost productivity like crazy, and get new lines up and running faster than ever.
Oh, absolutely. We're talking weeks, not months.
Exactly.
That ability to pivot, it's everything right now. And that pressure is why we're seeing this rapid convergence of all these technologies.
Right, the smart factory toolkit.
Yeah, you've got advanced robotics, incredibly detailed sensing systems, you've got edge computing for local processing, and then this robust connectivity driven by the Industrial Internet of Things, or IoT, and it all has to work together.
Okay, so let's start with the physical foundation, the machines, right? The robots. We hear a lot about robots and cobots making things more precise, more consistent. But let's get to the business reality of it. How does this really change things?
It changes everything, particularly when it comes to labor pressures. Look, the narrative is always about automation replacing people, but the reality is so much more, nuanced.
Yeah.
Industrial automation lets manufacturers scale their output, regardless of whether they can find enough manual labor at that exact moment.
That's the key, isn't it? It decouples production from the labor market. If you need to double your capacity, you can roll out robots faster than you can hire and train a whole new workforce.
That's the thinking.
But doesn't that just shift the cost? I mean, instead of wages, you're paying huge upfront capital costs, and you still need those really skilled techs to manage it all.
That is a critically important point. You're seeing a shift from what they call OPEX, or operational expense, to CAPEX, capital expense. And yes, while the robots handle the high-volume, repetitive work,
The boring stuff.
the boring but very precise stuff, skilled humans become absolutely essential for maintenance, for the complex programming, the configuration. The roles just shift. You're not doing the labor anymore. You're managing the performance of the labor.
So your most valuable employees become like systems integrators. They're complementing the machines, which brings us to these robotized cells. They're basically enclosed workstations, right? A robot, some tools, doing one job really well. But the real insight here isn't just speed, it's the consistency.
Consistency, and I'd add traceability. This is where automation just provides this huge leap in efficiency. If you have a problem, say a bad batch of 10,000 components,
A nightmare scenario.
a total nightmare. But with this, you can trace the data right back through the system. You know exactly which robot, which lot number, what recipe it was running, even the temperature in the room at that precise second.
So it's not just that the robot is precise, it's that it creates a perfect digital diary of its own precision.
That's a great way to put it, a digital diary. And that lets you pinpoint the deviation instantly. Was it a temperature spike, a change in the raw material? You fix it, and you make sure it never happens again.
Okay, but to get that kind of reliable data, the infrastructure, the power, the connections in that cell, it has to be just as smart. We saw vendors like Eaton working on this. Intelligent energy management, smart circuit breakers.
Yeah.
How does a circuit breaker become intelligent?
Well, the intelligence comes from putting data acquisition into these really low-level components. A normal breaker just trips when there's an overload. That's it.
On or off?
Right. But a smart circuit breaker or a distributed control system, it's always monitoring. It's reporting on current, on voltage, on temperature, constantly.
So the power grid of the factory is generating its own operational data.
Yes, and that data is the key to predictive maintenance. Instead of waiting for a motor to fail, which means unplanned downtime, the worst thing possible, the system can flag an anomaly, a tiny, sustained voltage dip.
Something a human would never notice.
Never. And it predicts that a component is going to fail in, say, the next 48 hours. So the maintenance team can schedule a replacement during planned downtime. It's about making uptime the default.
It's just another layer of optimization. That makes total sense. Okay, let's shift from the machines that do the work to the systems that see the work, segment 2. The factory senses. Advanced sensing.
This is crucial. I mean, the factory floor is no longer just relying on one measurement at a time. Manufacturers are blending all kinds of sensing solutions: optical, infrared, LiDAR, ultrasonic. They're all working at the same time.
So they're building this real-time 3D map of everything happening.
An instant map, yeah. They're monitoring performance, precision, range, everything, all at once. And you have companies like SCICOT that are real leaders here, developing these intelligent sensors and vision systems that can work at speeds the human eye just can't track.
And sensors play that dual role, right? It's not just about quality control, it's safety.
A huge part of it is safety. Of course, you have the basics like photoelectric curtains, emergency stops, but the real innovation is in dynamic safety systems.
Dynamic safety, what does that mean? How do you keep people safe without constantly hitting the big red button and stopping everything?
That is the million-dollar question. It's always this balance. Safety versus shutdowns. One of the best examples we've seen is the use of programmable warning zones around dangerous machines.
So it's not just a hard line you can't cross, there are layers.
Exactly. You set up an outer warning zone. If a worker gets close to that zone, the system might flash a light or sound an alert. Maybe it slows the machine down by 20%. But it doesn't stop it.
So it's a nudge. It's a, hey, you're getting too close, before they actually enter the real danger zone.
Precisely. That little nudge prevents them from accidentally tripping the main safety device that causes the hard shutdown. So the worker is safe, but just as importantly, you maintain operational uptime, you minimize those really costly, unplanned stops.
It's that same theme again. Optimization of both safety and efficiency through predictive data.
That's the thread that connects all of this. Continuous optimization.
All right, let's move up a level.
Yeah.
From the physical to the purely digital. The intelligence layer. And we have to start with edge computing.
We do. Edge computing at its core is pretty simple. You take the processing power of the brain and you move it from a central server room right next to the sensors and machines, right to the limbs.
Right to the edge of the network. And the big benefit there is speed, right? Especially for something like a high-speed vision system.
Exactly. I mean, if a camera on a line spots a tiny flaw on a product zooming past, you can't afford the delay. You can't send that huge video file to the cloud, wait for an answer, and get a command back in time.
The flawed product is already in the box.
It's long gone. By putting the AI model at the edge, the camera sees the flaw, processes it locally, and tells a reject arm to fire, all in a fraction of a second. That immediacy is everything.
And that processing power needs data. Which brings us to the industrial IoT and all that machine-to-machine communication. What's happening on the physical side of that, the wires and protocols?
So this is an important distinction. The protocols, things like Profinet or Modbus, they aren't new. They're like the established languages the machines use to talk. The real innovation is the physical infrastructure they're running on.
Okay, give me an example.
The biggest one right now is the adoption of single-pair Ethernet, or SPE.
A single-pair Ethernet.
Yeah. Traditionally, you needed these thick industrial cables with 4 or even 8 copper wires. SPE can send both data and power over just 2 wires, a single pair.
And why is that such a big deal on a crowded factory floor?
It comes down to cost and complexity. Less wire means lower material costs, lower installation cost, and a much smaller footprint. It lets you put a sensor somewhere you couldn't afford to before. You can just pull data from more and more places, more comprehensively.
That foundational connectivity, it's what allows the factory to become truly flexible. And that is a perfect lead-in to our next trend, which is kind of a historical reversal. High mix, low-volume manufacturing, HMLV.
HMLV, yeah. It's the dream, really. Being able to produce a huge variety of customized products in small batches, but with the efficiency of mass production. And it's funny because 100 years ago, Henry Ford basically rejected this whole idea.
Right. His whole model was about rigid consistency to drive down cost. Any color you want, as long as it's black. Why did that flexible modular idea lose out back then?
Because back then, flexibility meant massive cost and complexity. If you wanted to change from making Model A to Model B, it took days of manual retooling, reprogramming. You needed a totally different team of specialists. It was the complete opposite of a cost-effective assembly line.
But now, automation actually makes HMLV possible.
Yeah.
What's the tech that's bridging that gap?
It's that software layer we just talked about, the AI, the connectivity. Today, you can reprogram a robotized cell for a completely different task just by loading a new software profile. It's almost instant. So you can get that high-quality customization, maybe 50 different versions of a product on one line, because the hardware is flexible and the software is smart.
Agility is the new efficiency.
That's it. Agility has become the new metric, which ties perfectly into our final big trend, digital twins.
Ah, yes, the virtual factory.
Right. A digital twin is a living, breathing virtual copy of a physical system, a machine, a production line, or even an entire warehouse. It combines simulation with real-time data and machine learning.
So it's way more than just a 3D model. It's a dynamic simulation that's constantly learning. What's the real-world application?
Two main things. First, pre-production. Engineers can design and stress test a new production line in the digital twin, work out all the kinks before they spend a single dollar on steel. It just de-risks the whole process.
And the second use. When the factory is already running,
Continuous optimization. We saw a really great example of this with DigiKey's own distribution center. They use a digital twin to constantly monitor and simulate the flow of products.
so how does that actually work day to day?
Well, imagine they want to change the box size for a certain product. Instead of just trying it and hoping it doesn't cause a massive jam on the conveyor,
Which it probably would.
it probably would. They run the change in the simulation first. The twin shows them exactly how that new box size affects conveyor speed, sorting times, everything. It identifies a bottleneck before it happens in the real world. They are constantly fine-tuning their physical operations in the virtual world first.
That is incredible. The factory is basically in a state of constant risk-free improvement. So if we pull this all together, the smart robots, the dynamic sensors, edge AI, these digital twins, I'm seeing three pillars for this automated future. It's smart, it's agile, and it's safe.
And this isn't some far-off future. The adoption is accelerating so fast that the process itself is changing. We're seeing engineers and designers just bypassing the old supply chains. They're going to e-commerce partners like DigiKey to get these cutting-edge automation parts delivered in, 24 hours?
The speed of innovation requires a frictionless supply chain.
It does. You can't wait 6 weeks for a component when you're trying to iterate on a design in 6 days.
This deep dive really shows that the factory floor is becoming this hyper-connected, self-optimizing organism. Every single movement is a data point.
It is, which leaves us with a final provocative thought for you to think about. If manufacturing quality and efficiency are increasingly managed by AI at the edge, and they're constantly refined through these digital twin simulations, what non-technical human skills become the most valuable? Things like, complex system-level creativity or ethical design choices, or even just strategic risk-taking. What's our role when the machines handle the optimization?
The machine is optimized for production. The human is optimized for adaptation. That's a powerful idea. And a great place to leave it for today. Thank you for joining us for the Deep Dive. We'll catch you next time.